Good morning, class. Today is November the 29th, and it's Sunday. I'm doing it one day early because we have an energy audit on November 30th. So this is the video for December 1st. And okay, so first we'll go over homework 8 because we haven't done that yet. And problem 1, you had to calculate the capacitance of this capacitor, and that was just, plugging in for the values of permittivity and area and H. And that worked out to 9 farads. And the energy is 1/2 CV squared. And so that worked out to 45,000 joules. Which, when you convert to kilowatt hours by basically just dividing by 3,600,000, is 0.0125 kilowatt hours. And it sort of illustrates, how hard it is to store energy on a capacitor. This is, as capacitors go, a pretty good sized one, and you're only getting 1/100th of a kilowatt hour, and kilowatt hour, from your other homework assignments, that's 15 cents worth, and so this is like 1/100th of 15 cents, or less than a cent worth of kilo of energy. Now we're not covering in the course, but there's other capacitor technologies that are much larger, and they're called supercapacitors. And so people are looking seriously at using capacitors to store energy, and in fact I've seen applications in the field, certain niche applications where it's used because the capacitor can deliver its power so much faster than a battery. But going on, number 2, you had the linear generator, which I'm not going to draw the whole thing again. Okay, and you put a resistor there to get 200 watts, and that's 50 ohms. And so that means that I squared R, I has to be 2. Okay, and the force is I H V, where this is H. And if you plug that in, then it's 0.4 newtons. And the force of gravity, of course, is mg, where m is the mass of whatever object you're trying to lift, and g is the gravitational constant on Earth. And so if that is set equal to 0.4, dividing by g gives you a mass of 0.041 kilograms. Which, that's sort of interesting because it's telling you that, it's kind of easy to make electrical power. I mean, this is a 40-gram weight that you're lifting off the ground, and you're producing 200 watts. It's pretty impressive, actually, that with so little effort you can produce a fair bit of power. Okay, so that was the point of that one. Number 3, if the magnetic field is over here and the coil is over here, then d phi dz is 0, and so v is 0. The same kind of problem, number 5, if you push the coil back into the magnetic field, then d phi dt is opposite, and so v changes sign. Or polarity. So, that was the point of that problem, to make sure that you understand that, in one direction, phi is going down because you're leaving the magnetic field, in the other direction phi is going up because you're going into the magnetic field, and so the phi, and hence V changes sign. Okay, so that was those 4 problems, and I hope they provided some more illustration of how all this stuff works. And then the third one was this circuit L, R, and V here was given as sine omega t. So I is given for you, but I mean, you just know it's going to be a sinusoid. And so, all this is saying is that, I is going to be a sinusoid. It's not necessarily, ahead of time sort of, it's not going to be in phase with the voltage because of the inductor. And it's going to have some constant here. And, I had instructed you to, I know a lot of people did it with impedances. I'm not going to go over that. But let's just walk through it. So V, this is the source. That's equal to V across the inductor plus V across the resistor, just like in the example in the notes. And we already know the voltage across the inductor is L di dt. And the voltage across a resistor is, of course, just IR. And so here I prime is equal to omega A root of sine is cosine omega t plus V. And so you plug that in there, you plug that in there, and you get a differential equation because, of course, this is sine omega t. And I'll write it out. So you get the sine omega t is equal to AR, writing the resistor part first. Okay, we're doing one step ahead. Sine omega t plus phi, that's the resistor part, plus A omega L cosine omega t plus phi. And you were supposed to use your, sine of A plus B is sine of A cosine of B plus cosine of A sine of B, and the same thing for cosine. And if you then plug it in, and let me see if I can collect terms in real time, you get the sine omega t is equal to sine omega t times AR cosine phi, okay, minus A omega L sine phi plus, collecting the cosine omega t terms, cosine omega t times AR sine phi plus ALW cosine phi. All right, and so the point is now you look at this and you realize that this has to be 1, right, to make this identity work, and this has to be 0. And so, setting that to 0, so that means that R sine phi is equal to omega L cosine phi, and so tangent of phi is equal to omega L over R, and you were given, I think, 60 hertz, yeah. Yep. And so omega is 2 pi times 60. L was given, R was given, and so basically, oops, there's supposed to be minus sign here. So that's equal to negative 0.377. And so phi, taking the arctangent of that, is negative 20.7 degrees, and cosine of phi is 0.936. Okay, so this problem was meant to illustrate, cosine phi and how you calculate it in a real circuit, and that for sort of normal size inductors and capacitors, you get something that's still pretty close to 1, really, if you think about it. See, phi is 20 degrees here, which means that I and V are pretty far out of phase, really. But you take the cosine of that, 0.936, it means that that's your power factor. And so when you plug it into the formula for power, IRMS, VRMS power factor, cosine phi, it's not that different than a purely resistive load. Okay, so that was the homework. Let's go on to new material here. Today we're going to cover 5 energy efficiency principles. And let me just choose focus. Okay. So now energy efficiency means doing the same thing with less energy, and we'll go through 5 examples, and you'll see that in some cases, well, in one case anyway, you're not exactly doing the same thing. It depends on how you define what the same thing means. So the first, and I sent this in the post yesterday too. The first thing is driving slower. Now, this is important at highway speeds. Okay, and we'll show that one. That one's for transportation, and I mean, of course, we went into engine technologies a little bit, and how the efficiency of an engine itself is improved. You could also go into how the efficiency of the car body and the aerodynamics and stuff like that. But this is, more kind of an operational efficiency. Then the other 4 are, well, the next one is for industrial systems, and it's controlling pump and fan systems with variable speed. Okay, and we'll show how that works. Number 3 is sort of general to, so this is transportation, this is industrial. Number 3 is kind of a mix between industrial and residential or commercial. It's I mean, it's not an efficiency, well, you'll see, I'm going to describe it as an efficiency principle, replacing electric resistive heaters with heat pumps. Which, as part of this is the concept I'll just write out COP, and we'll describe what that is in a second. The fourth one is, sort of purely kind of residential or commercial. It's calculating heat loss. Conductive heat loss, sorry. With R value. Which some of you may recognize as, something that represents insulation. And number 5, heat loss due to, and I'll put just ventilation. And both of these are, the efficiency is not stated. Of course, the efficiency in this case would be to increase your insulation to reduce heat loss. The efficiency in this case would be to reduce whatever ventilation you're performing. And there are remedies. We'll see if I have time to this if you have to ventilate, and we'll talk about that in a second. Okay, so these are the 5 energy efficiency principles that will be covered as part of course material. There's more in the notes, but this is what I will expect you to be able to, answer questions about in the quiz. All right, which we'll talk about the quiz on Thursday. So the first one, and the book goes through kind of a little bit of a meandering derivation. And it's kind of more simple to understand. And I just let me just write it down, because in principle you have to think about it a little more carefully. But I think you can get the concept across really easily. So car. Now I'm going to draw the car moving that way. But I'm going to think of it as the air going that way with the velocity v. And if the air is blowing out at the velocity v, you know that the power in that wind, in that air, in air movement, is proportional to v cubed. We learned that in almost the first class. And so at highway speeds, the primary thing that the vehicle is overcoming is air resistance. And so you have to be a little careful here, because this is the airspeed, so to speak. I'm not going to get into those deals, and so you sort of assume there's no wind going on here. But what the vehicle is overcoming, where the energy is going in forcing the vehicle forward, is in heating the air, basically, and overcoming the wind resistance. And that goes as v cubed. And so that means that this is also the power of the vehicle, right? The engine power that you're supplying is approximately going as v cubed at highway speeds, because that dominates. Now the distance you go is proportional to v, of course, right? If you go faster, you go longer for the same amount of time. And so the power, or the distance over the power goes as v over v cubed, or is proportional to 1 over v squared. And that then is proportional to the miles per gallon. Which most of you are more familiar with. So at highway speeds, and so I'll draw a couple of highway speeds, both of which are mostly illegal. But just to illustrate the point, going 70 and 80, miles per hour, your MPG, your miles per gallon, will go roughly as 1 over V cubed. And so at 70 miles per hour, if your MPG is 30, right? Then at 80 miles per hour, okay, you can write this very easily. It's basically 30 times 70 over 80 to the third, and that works out to 23. So if you're driving somewhere on the highway and you go 70 miles per hour and your vehicle gets 30 miles per gallon at that speed, all right, if you increase your speed to 80, you will get only 23 miles per gallon, roughly. And now, so basically you can save gas by driving slower. And that's great. And we can calculate, for 100 miles, so 100 miles over 30 miles per gallon, right, that's a 70. All right, so that trip then costs you 3.33 gallons, and at $2.50 per gallon, then that trip costs you $8.33. And at 80, all right, that same 100-mile trip at 23 miles per gallon took 4.35 gallons. And at 2.50 a gallon, that then cost you $10.87. So if you were to take the same 100-mile trip going 70, you would save, whatever that works out, about $2.50 at that price of gas. And so, this is, energy efficiency in a sense, okay. Now, you aren't exactly accomplishing the same thing, of course, because 100 over 70, right, that is 1.43 hours. And 100 over 80, that is 1.25 hours. All right, so a way to think about it is that, okay, again, energy efficiency is, okay, doing the quote-unquote same thing using less energy. Now, this is an example where if the same thing is going 100 miles, all right, you clearly, save a lot of energy by driving slower. If the same thing, though, is going 100 miles in 1.25 hours, well, then you haven't accomplished that. And so, it comes down to what you define. And you can think of it as, okay, this has cost me $2.50, and I got there, whatever this works out to, that's 15 minutes, that's less than 30 minutes, so, somewhere around 10 minutes, okay? So you by spending that $2.50, you got there 10 minutes faster. And people could calculate that, oh, that was worth it to me. All right, it was worth it to me to get there 10 minutes faster, this 100-mile trip, and spend $2.50. The point is now you can perform this analysis, and this borders this goes between the fields of energy efficiency and energy conservation, in the way I think about it. Conservation means conserving energy, and you because you haven't done the exact same thing, meaning get there in the same amount of time, you are conserving energy, which is where you're using less energy but not necessarily accomplishing all the things that you were before. All right, I'm not going to belabor this. I just wanted to go through the analysis and how you understand it. And it's just, it's just that your miles per gallon goes as 1 over v squared, and it's a simple calculation that, the distance you go is proportional to the velocity, of course, whereas the power required to do that, because of the power in air movement, goes as v cubed, and so v over v cubed is 1 over v squared. All right, so let's move on. All right, number 2. All right. Okay, so this is a little bit. I mean, it's not really more complicated. It's along the same lines. Okay. Let's say, and I'm going to just use an example to illustrate this. Let's say you have some type of well system with there's a source of water that's variable. Okay, sometimes it's fast, sometimes it's slow, and so there's a water level in here, and this water is coming from somewhere you don't know where and you don't know why, but your job is to pump it out of there using some pumping system. And how your pumping system works is 2 ways. The first way is your well can have a little float here. Okay? There's a float and a switch there, and that well, I'll just draw it like this. That turns your pump on. So this is on, off. So basically, the idea is that when that water gets up to that float, it lifts it up and it switches the pump on. Okay, and the pump pumps the water off until it drops back down below the level where it switched the pump. And the second way is you have a level meter, okay, that controls the speed of the pump. So in this case, the pump runs at full speed, on, off, on, off. In this case, as the level rises, the speed goes up. As the level falls, the speed goes down. And you are adjusting the speed to try and keep the level at a set point. All right, and so we can look at the 2 situations. Now, in the first situation, our power versus flow can be analyzed this way. All right, when the pump is on, we are at 100% flow, and I'll write that as 1, and our power is the full power of the pump on. And when it is off, it is 0% because it's off. And so what happens is that as the water level rises and falls due to this incoming flow varying, okay, the pump turns on and off and on and off, and basically it's going between these 2 points here like that. And so we can draw what's called a load line, which is power versus flow like that. And F here is the duty cycle. So if the flow rate and everything, if the duty cycle is such that whatever the duty cycle works out to be, basically you can think of it this way. In this situation here, okay, the pump turns on, the pump turns off, pump turns on, the pump turns off, etc. And if you take this and divide that by that, that's equal to F. Basically, it's the ratio of time that the pump is on. So this is situation 1. Now situation 2, all right, is different, because what you know now is that if I vary the speed of the pump, okay, because the flow in any fluid, whether it's water or air, and that's why I say pump or fan systems, you know that the power is proportional to the flow cubed, right? Because it's proportional to the velocity cubed. And so it will follow a power versus load curve that goes as P on flow cubed. So you can see already, and sorry I didn't draw them to the same scale. Let me see if I can fix that over here. Put that point over here so it kind of matches a little bit. Okay. All right, and so, well, that's very low average, but I'll put it over there for now. And so what you see is that the two power versus flow or load curves are very much different. In the case of on-off control, the power versus flow is linear, right? Because it's just the duty cycle times P on, whatever F happened to be. Whereas here, okay, as I vary the speed, it goes along this flow cubed curve. And so if I have an average F here, then that power is P on F cubed. So the power, so P1, or let's call it P2, or yeah, P1 minus P2. And you can sort of just see you're going to go down is equal to P on F, that's this one, minus P on F cubed, or P on times F minus F cubed. And so, you know, if I take this and draw it right here, okay, you can see that depending on what F is, right, you get a savings of putting it on a speed drive, because you're going from linear to cubic, and so you get a power savings of F minus F cubed. Now, you can see that very quickly that if my pump is always on, I don't save any power. And in fact, you lose a little because it takes a little bit of power for this drive to work over here. So you don't want to apply speed drives in situations where the load is continuous. But if my average duty cycle or our average speed is around 50%, and in fact you can calculate that F minus F cubed, of course, versus F, it's 0 at 0 and 0 at 1, and it goes through a kind of a minimum like that, and that maximum point is, you can just work it out pretty easily like taking the derivative, is 0.5, is 58%. So you get your maximum savings if your duty cycle is 58%, and that savings is then, I worked it out here somewhere, 38.6%. Okay, so going from this on-off control to speed control, you can save almost 40% off the operation of your pumping system. And this principle applies to various systems. It applies to fan systems as well. If you have some sort of cooling system with the fan, where you're trying to achieve a set point by turning the fan on and off, You can achieve great energy savings by instead adjusting the speed of the fan to match whatever you're trying to do, and get close to 40% savings in an optimum situation. Okay, so moving along here then, so that was number 2, speed control. All right. So number 3, okay, this is sort of closer to home now because you did your homework 9 and so learned a little bit about your heating costs at home and things like that. Now, what I want to do here is talk about the principle of it is called coefficient of performance. Performance. Usually referred to as COP. And if you have your house here and you have an air conditioner, okay, what that air conditioner is doing in the summer is it's pumping heat out of your room, okay, and if you've never done it, okay, someday, I mean, if you're able to stand here outside your house where the air conditioner is, feel, there's a fan in here blowing air out, and if you feel there, you'll feel warm air because it's pumping heat out of your room, and so making it cooler here. Now, the principal coefficient, okay. Now your air conditioner has, a cord here, and it's basically plugged in there, and so there's an electric power required to operate this thing. And if Q heat and W electric are the same units, for example, kilowatt. The COP is Q, your heat pumping, divided by W electric, and it's usually greater than 1. In fact, it's always greater than 1 unless there's something wrong with your air conditioner. Meaning, if I have to pump 3 kilowatts of heat, okay, now it's a form of power, right? It's the flow of heat. Actually, you're supposed to put a dot there or something like that. And in fact, let me just rewrite this as W heat, so there's no heat confusion. It's the power and the heat flow. It can be measured in kilowatts, just like electrical power. That if I have to pump 3 kilowatts of heat out of my room, okay, a typical air conditioner will require only 1 kilowatt of electricity. And so my COP, it's kind of like, I don't know, it's the right way to think about it. You have a valve here or something like that requires a certain amount of power to operate, and and you're pumping heat out with the system. Now, what's inside this black box is, that's the vapor compression refrigeration cycle, and there's a lot behind that, and it's an interesting thing. There's just no time for me to try and teach that to you, but I wanted to teach you as a black box the concept that, okay, the COP, which is the I'll rewrite this W heat. That you can, with less electricity, you can pump more heat. Now, okay, so I talked about replacing electric with heat pumps. Well, okay, so this, okay, you don't do this, okay, there's other ways of doing it, but this is, if I took this, let me see how I can designate one side like that, okay. If you took this air conditioner, in principle, okay, if you flipped it around during winter, right, Now, I'm not recommending that. They're not designed to operate that way. A true heat pump is designed, it has switches and valves inside so that it can flip, which way it's pumping the heat. But, this is just an imagination to illustrate the principle. If I took the room air conditioner and I flipped it around, it would be pumping heat in, and for roughly the same COP. Okay, W heat over W electric would stay the same at about 3. Now, if instead you have a little electric heater, and they're usually called resistive heaters, its heat is precisely equal to the electrical power in. All right? It's just a resistor, basically, or of some sort. And so whatever electrical power you put in, you get that much heat. And so if your air conditioner is 3, okay, that means that, okay, if this is W electric of pump, and this is W electric of resistive, it means that for the same W heat, W the heat pump, is 1/3 W the resistive heater. Okay, so it's a common recommendation, and in fact I made it to one of the students who, after telling me what his heating costs were in the summer, I was like, oh wow, electric heat. And so, if you're heating your house with a bunch of electric floor heaters, you can save 2/3 of your heating cost, whatever that worked out to be when you calculate it in your bill. So, and there may be other students out there in the same situation that are heating their domicile with electric floor heaters. If you instead, okay, now you don't do this, you buy a unit designed for the purpose. It's called a ductless heat pump. You'll save 30%, 2/3 savings, 67% savings. Okay, so that's what I was going to go through there. I was also just going to say, this is the same thing that's in your refrigerator. Okay. Okay, it's basically, there's some coils in there, and there's, basically it's using this to pump heat out, and it plugs in. Of course, you know that now, most of you. And so a refrigerator also has a COP. Which is the ratio of the heat being, on average pumped out of the refrigerator divided by the average electrical power. Okay, so let's see what we're doing for time. Good. The next two I can put on the board at the same time. It'll go quicker. All right, number 4. All right, so if you have your house here, all right, usually there's insulation in the walls, insulation having an R value. And I'm going to illustrate how you use R value just by doing a calculation of the heat loss. So if there's an outside temperature lower than the inside temperature, all right, there will be heat leaving through conduction, and that W heat in BTU per hour is equal to the square footage, all right, and I'll calculate that in a second, times delta T, or let's write it out, it's T out, T in minus T out, over R. So this is the area, this is the different, and this is in Fahrenheit. All right, and I guess my apologies to overseas students who aren't ever used to seeing square foots in Fahrenheit. But it's just so common here that this is the way we teach insulation with using R value. And I can give you an example. Let's say your house, let's say it's, you know, roughly, what did I use here? Let's say it's like 30 feet by 30 feet, and the walls are 10 feet high. So the area A is approximately equal to the walls 4 times 30 times 10, that's the walls, plus 30 times 30, that's the ceiling. Now usually the ceiling has a higher R value, more insulation than the walls, but if we assume it's all the same, you know, that works out to what is it, 2100. And so your heat loss in BTU for this situation, if I have 2100, and let's say that this is you know, like this is 70 on average, and if this is what did I use, 35, well, okay, let me use 45, right. If during winter the average temperature outside is 45 degrees, the average temperature inside is 70 degrees, this is 25 Fahrenheit, that's the difference. And let's say your R value is 15, so R15. Then that works out to 3,500 BTU per hour. And all winter, so that's 3,500 times, and I'll just use 6 months times 30 days times 24 hours in a day, and it works out to 15. And you know, I'm going to start well, I'll write it out. 15 million BTU, which is 15 MMBTU. So that is telling you that if you're fairly well insulated with R15, your heat loss during a winter, where the winter's average outside temperature is 45 degrees, is 15 million BTU or 15 MMBTU. Now let's do situation 5. So, okay, what is the energy efficiency? The energy efficiency increased the R value. Now, if you have no insulation, then it makes sense to do. Economically, it rarely it doesn't save you enough money. In your other homework, I think you have to go through it. Yeah, so this is you know, kind of around $15 or $150. Because the usual price for gas, for example, is $10 per MMBTU. So it's somewhere around $150 what it's costing you, that heat loss. Now let's look at the situation where your house has an exhaust fan. All right, which is typically, you know, like might be in a bathroom or something like that. And let's say that bathroom exhaust fan is exhausting 100 cubic feet per minute, which is a standard designation. This is CFM, cubic feet per minute. Now the heat capacity of air is 0.018 BTU per cubic feet per delta T again. Now I have to explain that. So basically what's happening here is that you're putting out air at 70 degrees, because that's your inside air. Now, basically, every time someone opens a door, or through cracks in the window, or through whatever other, basically points of entry air can come in, air is coming in at average 45 degrees. It has to, okay, because, you can't depressure, you can't produce a vacuum in your house, okay? The exhaust fan is pumping the air out, air is going to come in somehow. If nothing else, every time someone opens the door, the air will just rush in. And so delta T is the difference between inside and outside again, because the heat capacity is how much heat it takes to heat up that air that's coming back in. Okay, so the heat loss then of this situation is equal to 100 CFM, which is a standard bathroom exhaust fan. You have to multiply times 60 minutes per hour times 0.018 times 25. And if you multiply all those together, it gives you 2,700 BTU per hour, which all winter is 12 MMBTU. All right. So I've illustrated two ways you lose heat from your house, for example. One is through conductive loss through the insulation. And if you're insulated well with R15, which is reasonably high insulation value, you lose 5 MMBTU every winter. And so that costs you around $150 in heating costs. All right, if you have a bathroom exhaust fan that's running continuously, all right, you lose almost as much, 12. With one little exhaust fan, that's a tiny exhaust fan, 100 CFM. And that's like one of these little bathroom exhaust fans up there. So the message is that, okay, if I were to try and fix this problem, it would cost me plenty to go up in the attic or in the walls and increase the insulation. Okay, if I tried to reduce this by 20%, it would cost me thousands and thousands of dollars. But okay, what can I do about this? Okay, for the same amount of money, in fact more, because I can turn it off. And so one common recommendation is what's called curtailing the ventilation. Now, if there is ventilation taking place somewhere, you have to understand why. Okay, why is it taking place? And a bathroom exhaust fan, the reason is obvious. But okay, for example, we run into the situation a lot where the fan's left on continuously, as shown here. It doesn't need to be on at night when no one's there. Okay, and in fact, the main recommendation is to put that on an occupancy sensor. Okay, meaning every time someone comes in and uses the bathroom, okay, it goes off and it stays on for about 10 minutes then after that. And so you can reduce this by 90%. So if I wanted to reduce this, okay, it would cost me thousands and thousands of dollars. Okay, and I would get less reduction. But if I wanted to reduce this, I could pay $20 for an occupancy sensor and put it in and save 90% of it or so. All right, so those were the 5 principles I wanted to illustrate in this last lecture we have. And I think it worked out pretty well. We're at about 55 minutes, that's good. I think that when these videos get, too much longer than this, it becomes sort of burdensome to watch them. And I hope they haven't been. I hope you've been having fun. It actually helps me frame the lectures more because I have to think about the time frame and things like that. Now, the next lecture, there'll be also a video on Wednesday where we have a review for the quiz, which is a week from Tuesday. And then the last class, we'll also have a video going over the final project again, and of course the GroupMe sessions. Okay, that's it. I'll talk to you on Tuesday during GroupMe.